Okay. It's really an honor being here. I'm also a bit humbled because I know there's so many of you out there, you know so much about this stuff. So I'm speaking to a very informed audience. My presentation, the challenge here is a bit like give a presentation, on science or something like that, and it's very broad. Give a talk on AI, it's very broad, yeah. So what I'm going to do is I'm going to frame it a bit, and then in the middle section, there's just going to be a lot of animated videos with reinforcement learning, and apologies if someone's seen those before, but I do think they're highly relevant, but they're also a bit entertaining, yeah. So let's just jump right in. My clicker is working. Yes. Do you all feel like this? That we have a Sputnik moment? I do. Just want to frame it a little. This is only the second time in my life where I feel like I wake up and I'm like, wow, the world just changed. And I can sort of even remember, a few weeks ago or whatever, months ago, when it hadn't changed yet. Yeah. I did my master's thesis, late 80s, on hypertext. I wrote a browser. I didn't call it a browser because I don't think I knew that word at that time, but 89. Click, you have a back button, you have a history, and I put my own thesis in there and I could browse it. Yeah. Went to a workshop in the US. I'm from Denmark. Went to a workshop in the US. We were 2 Europeans and a lot of Americans who all went to the same school and knew each other. So we're like so outside the crowd, yeah. So I went and talked to the other guy. It was Tim Berners-Lee, and he had some ideas, and I'm like, oh, I have the same ideas. So I went down and on several occasions to CERN to work a bit with him. I finished my PhD in '92 on the idea of clicking on a link, run a script on a server and get some dynamic generated page back. And we all like, don't know what to do with this, but we'll figure it out one day. What happened, at that time, saw the first conference call for papers saying www. something, yeah, the 3 W's, yeah, and it's like, oh, that's interesting. Drove down 101 on a trip here and saw an IBM billboard that says big IBM, blah, 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 enterprise this, that, and then at the bottom it said www.ibm.com. And this is so early that my company got a 2-letter domain name, yeah? And we had no idea how much that would be worth until nowadays, where all those are, taken, yeah? So it was a moment where everything changed. Like you went from, you had to go to the library, you have to travel across the world to meet people, to understand what they were doing, or you have to subscribe to magazines that published science or research that was like, a year old, yeah? And now you could click and you could share stuff, yeah? Right now we have the same moment, yeah? We have all this stuff here happening. Large language models, of course, like just absolutely redefining the word at this moment. Image generation, video generation. We have, computer vision progressing, certainly. And we have not even seen the explosion there yet. When you start mixing large language models with computer vision, that's gonna go crazy. Protein folding. I had a bachelor in chemistry because I wanted to be a geneticist, but I wasn't smart enough for that. But I actually started with some folks who went out and founded a company that they sold after 3 decades doing protein folding with 50% accuracy. And then AlphaFold, bunch of computer scientists spending 2 years and getting 95% accuracy. Yeah. Changing the world, yeah. Music, let's not go into that. AlphaZero is the Go playing system is an old story, and just all this stuff, yeah. So we look at this, and then of course I want to remind everybody that the Sputnik moment was really just the beginning of it, yeah. 12 years later, this happened, yeah. And I'm going to throw this out to you. Don't try to answer me. I do get a lot of answers to this question, which is, so what is the moon landing for us? What is the moon landing for AI? Yeah. And some people don't know. I don't think I know. And some people have ideas, but I think I don't think they're right. Yeah. I can tell you that very early on in 92, 93, working on the World Wide Web, I mean, like social media is like, I mean, like that was not the idea. Yeah. Yeah. Everybody was focused, and I'm going to get back to that in the end of my talk, but everybody was focused on building browsers and servers. Yeah. Because that was the business. Yeah. But where were the $1 trillion generated? Somewhere else. Remember that. Okay. Just going to talk a little. I'm going to give some examples. Now, the real reason I'm going to show you this talk is I saw a tweet a few days ago that upset me a lot. The tweet was, "Long live LLMs, and finally reinforcement learning is dead." I was like, no. Yeah. And then I saw another tweet as recent as yesterday. And I'm talking about not random people, it's people who are supposed to know, with a lot of followers listening to them, saying that they got so mad every time people say chatbot and chat GPT, they should just say LLM because that's what it is. I'm like, not entirely. There's more to the story. Yeah. So let's talk a little about reinforcement learning and sort of intelligence derived through this process that we see in biological systems. Yeah, where we have this need to acquire energy to maintain the molecules of life. Yeah, that's sort of the whole idea. Yeah, and avoid becoming that kind of piece of energy for other pieces of life in that process. Yeah, and become more abundant and be careful of physics and basically all that stuff that is sort of required to survive. Yeah, and nature also sort of helped us with this thing. Yeah. Had to create this thing so that we could actually be intelligent. All these different species out there have this kind of system that I call infrastructure to just build up these intelligent systems that are in various degrees in living organisms. Yeah. So behind all that, at both at a I would say at a meta level and at an individual level, yeah, is reinforcement at work. Yeah, so at the meta level, reinforcement learning is evolution, and at the individual level, it's learning. Yeah, but I will sort of stretch things a bit here and say, well, let's all throw it into the same bucket. Yeah, and call it reinforcement learning, nature's method of getting better. With this idea of observing, taking action, and take the rewards or penalties from that. Yeah. So I'm going to show you a small video of a chicken learning to cross the road. This is the old pixel observation approach. Just observe pixels. You have 4 actions you can take: left, right, forward, backward, and then you have reward signal where the chicken gets, a negative hit from being hit and a positive one for picking up a package. Yeah. And then in this video, starting from scratch, you'll see the chicken just really randomly explore and trying to figure out what's going on. But in a few seconds, it's going to catch that package up there, which is a good thing. And then it's going to get run over, which is a bad thing. Yeah. So in 5-10 seconds or whatever that was, it already, got 2 pieces of information. Yeah. And after half an hour, it actually gets pretty good from scratch, tabula rasa, picking off packages, avoid a few cars, but not really all of them. Yeah. So it's not really perfect yet after half an hour of training. But watch, we let it train for 6 hours and it becomes superhuman. These packages and cars, they're all just random. It's not like it learned a particular pattern. No, it learned a general policy of avoiding cars and picking up packages. You know why we had put the packages in there and not just the cars? To get it to move, yeah, because there are always more packages in the future than in the past. Yeah. It's one of those funny things about reinforcement learning. You always have, sometimes you have to be a little circumspect to get the agent to do something. Yeah. Anyway, I'm gonna run from some cute little examples of, you know, this is all done using the PPO algorithm. And for developers, this is all open source. ML for machine learning, ML agents on GitHub, very, very popular repo. Anyone who's a programmer should. People ask me always, which book should I read about this? I'm like, go and build something instead. Yeah. So you can go and build all this stuff here. It's there. Learning, you know, like a toddler. Anyone who had a little child, they recognize that it's really hard to keep all those joints controlled. Yeah. And it's even harder for them to walk on an uneven surface. Yeah. So this is all this good old tabula rasa method. You just train from scratch every time. But we quickly found that that there are certain benefits to look at to look at how we go to school. Yeah, like first grade, second grade. We just don't. Very few people skip all that and go right to high school or college. Yeah, and there's a reason for that, and that is that these neural nets inside our minds and inside computers, they act somewhat the same. They if you start easy and make it harder and harder, they tend to be more efficient. So this is an example where it's a push block example. We just train a lot of agents in learning to push a block into a goal destination. And then we make it a little harder. We put an object in there that they have to navigate around. And then we make it even harder then, because now they also have to climb a wall to get over there. So they have to push a block to use it as a stepping stone. Yeah. And when you go through these stages of a curriculum, you actually end up with a much more efficiently performing model, which is, you know, it's interesting because that's how we work too. So we learn a bit from looking us around, look at nature. There are other examples. Attention is one of them. Look carefully here. The idea here is that the blue agent has raycast sensors. So the blue agent is look, you can see all the little arrows there. Is actually trying to look around. Yeah, it's a sensor. And when it's pushing the block through the hole in the wall, it's narrowing the use of those sensors. It goes from 360 to like 90 degrees. Yeah. And the interesting part here is that the focus of those sensors, that was reinforcement learned, yeah, not engineered. Yeah. So it basically is, of course, optimal to have a 360 view when you search for the cube you're going to push. And then when you get close to the hole, you spend all your sensor energy on the surroundings just around that hole. This was a simple inspiration when I worked at Uber on self-driving cars. We had, I believe, 16 cameras on those cars. We had a 3 kilowatt 9-blade computer in the trunk. And I noticed that we had as many cameras looking backwards as forwards. And I asked one of the hardware engineers, why do we have evenly distributed cameras? And they look at me like, of course, this is a nice design. And I was like, yeah, but when I drive forward, why am I spending half of my processing power looking backwards? Because I can't really do much about what's going on behind me. And everybody looked at me like, this is the way we build it. Yeah. This little example here is sort of where you actually have to figure out how to spend your resources wisely. Yeah. So this is the idea of attention. You all heard that in large language models too. Yeah. It's everywhere. Yeah? Here's an example that the agent learns which projectiles to care about, the ones that may hit it. Yeah. Ignore everything else. So in this case here, the agent could not process the whole world view. Yeah. It would basically be too slow. Yeah. What it does is that it actually learns, first and foremost, which projectiles matters and which do not. Yeah. Another example of attention, which is something that is very important in biology. Otherwise, our brains would be like ginormous, yeah, because we need to spend so much energy processing 360 around us, and that makes no sense, yeah. Let's jump from individual agents to multi-agents. This is a very simple example of two agents cooperative. So I have a joint objective. The ball should not hit the ground, so let's play together and make sure it doesn't hit the ground, yeah. Or we can have two agents playing against two other agents on two teams playing, indoor soccer. It's kind of fun to watch. They play from scratch again, and they develop some interesting behaviors, maybe more clear here. Actually, what happens is that there's a tendency for one of the agents to always pull back and be a defensive player. It's nothing we told it to do. Yeah. So when you go into multi-agent systems and user reinforcement learning, you see this very interesting emergent behavior coming. You know, I mean, like I didn't know that this kind of dynamic defensive play was important. Yeah. Here's another example. It's a simple example of one agent pushing a block. But what if I make that block very heavy and hard to push? Then I need to have 3 agents to put their forces together to push the block. Yeah. And what I want to show you here is the dance, because that's what we noticed. We put 3 agents together, and after training them in 1 million episodes or whatever, I can't remember how many, they do this dancing thing. And everybody's like, why are they doing all this stuff? And it's just get the job done. Yeah. In fact, of course, I don't know, but I think I know that they're communicating. They're trying to negotiate to work together on one block, on pushing one block. After they do the dance, they actually do the push, and we found that they have 2 ways of pushing. They either form a wedge, so 2 guys or 2 agents next to the block and then 1 behind. So they create a wedge and push, or they stack up. Yeah. But they do the dance, and then they choose one of these methods to push, to jointly push a cube. And that's another example of emergent behavior coming up. So we saw the defensive player in soccer example, and here we see some kind of planning taking place. Yeah. If you do bigger, I have some more complex examples of, we did some dodgeball examples and capture the flag examples. The problem is with those videos is that you have to look at them for an hour or 2. And then you start seeing very systematic behavior, but it's hard to sort of show to an audience like you in 1 minute. So, but it's fascinating to see all this stuff. Yeah. I want to jump something interesting with all this stuff here, where so far it has been just extrinsic values all the time, which is essentially the idea of scoring points. Yeah. I mean, like collect these packages or play the ball so that it doesn't hit the ground, something like that. Yeah. So it's external it's specific to the environment that you're agent in. But nature equipped us with all these other things like curiosity and impatience and happiness and love and all these other things that apparently they're pretty costly from a biological perspective. And nature is not doing anything costly if it's not needed. So it's apparently very, very helpful for our survival. So why don't we look at some of that? Yeah. And we try to find some use cases where traditional reinforcement learning just breaks down, because it's just random exploration. It's just not going to happen. It's never going to figure out this complex chain of things it has to do. Yeah. So we found some what we call improbable scenarios. Yeah. In this case, what I'm going to show you is an example of an agent entering a building with rooms. Of course, it starts from tabula rasa, so it knows nothing. Yeah. So it enters this building with rooms in. In one of those rooms, there's a button. It needs to push that button, and then a pyramid will appear. A pyramid will appear in another room. On top of that pyramid is a gold bar. It needs to knock over the pyramid to get the gold bar. The gold bar is the extrinsic value. That's the point. It gets a point for every gold bar it can collect. Yeah. And to make that happen, we need to look at intrinsic rewards. Yeah. And we look at sort of the idea of curiosity, and curiosity is in here. It's like in machine learning, we always want to make the error as the predicted error as small as possible. Yeah. But what if you just flip that and put a minus in front of it and say, I want to look around, and the next thing I'm going to do as an agent is the thing where I will be most wrong in my prediction of what's going to happen. Yeah. So you just learn to be curious. Yeah. And look what happened here. This is without curiosity. The agent is randomly exploring, but the chicken randomly explored, but very quickly learned to pick up packages and avoid cars. Yeah, it was very dense event space. Yeah, so it could do that. But here we have a long chain of stuff. Yeah, it will never learn it. Yeah. Look what happens if I run it without extrinsic values. Yeah, so I have no rewards function that says collect gold bars. I just say, be curious. Yeah, and it will, you saw it quickly move from one room to another room. It doesn't really dwell too long on something. And then it starts identifying things that, in this case, something happens when I hit these pyramids really hard. So maybe I can knock them over, whatever, yeah, going on. And then when you put it together, it becomes sort of very driven, going from room to room, searching for the button, hitting the button, searching for the pyramid, knocking it over, and right there in a moment, now getting the reward, yeah, from picking up the gold bar. Yeah. So curiosity, I can tell you, you can run 15 million episodes and it will not figure it out. You throw curiosity in there, 10 to 15,000 episodes, and it's perfect. Yeah, that's a dramatic improvement. Yeah. So curiosity is a really good thing. Actually, a lot of video games can be played using curiosity alone. So using intrinsic values. Don't care about collecting coins or points or whatever. You know what's the most common thing in video games, in most video games? Levels, yeah. You go from one level to the next level to the next level, yeah. That in itself is gonna be a vehicle for curiosity, yeah. The agent wants to finish a level to get to the next level very quickly, and we have tried this. It will play some games not to score points, but only to get to the next level. And by the way, most people playing video games that they are very level-based, Candy Crush has like 12,000 levels or something, and people just play and play and play just to get to the next level. Doesn't matter. It's actually the satisfaction is to get to the next level. It's an intrinsic value. Yeah, it's not I'm collecting Bitcoins and I'm going to get very rich from this. Yeah, no, I just want to get to that next level. And that's why, King Studios, they keep publishing new levels to Candy Crush, because that's all people want, to get to that next level. Yeah. By the way, tons of biology and psychology in video games. Yeah. Let me show you Pubble. It's a virtual dog or virtual puppy. Just reinforcement learning, no animation engineers, no game engineers, no nothing, just from scratch. Rewards function is fetch the stick. The thing can barely walk. Yeah, it first had to learn to walk. So you run, a massive amount of puppos that will learn to walk, and then you can play it like this. You can, it will give you the stick. You can throw the stick with your mouse, and we'll bring it back. It's entirely reinforcement learning driven, using a physics engine, and then we put a bit of music on to make it more fun. But that's it. Yeah, this is learned from scratch, and the only rewards function is to bring back the stick. Yeah. And you can do it. You can play it on a phone too. Yeah. The idea with this is actually to make people be like, oh my God, this is so cute. This is so fantastic. It's just like a real dog. I want demoed on stage this small thing here. And what I had practiced was to move the stick left and right. Because then, because of the physics, I could get the dog to roll over. And I wanted to sort of show people that by moving the stick, I can get the dog to roll over. In one of those occasions, instead of getting it to roll over, it grabbed the stick, turned around and dropped it. And I was like, okay, that was not planned. Apparently the rewards function is very strong to return that stick. Yeah? So it does sort of give you some ideas that you look at some of this behavior and it's extremely recognizable. It may sometimes remind you that maybe dogs, maybe we don't have like a billion of neurons that do something to fire, but maybe sometimes it's a very short path that fires. Yeah. In this case, to grab the stick is probably not a deep, thoughtful thing from the dog side. It's a very short circuit in its brain where it really wants that stick, because getting the stick allows it to get my attention when it gives it back to me. Yeah. So funny to see a stupid little laptop-based dog or iPhone-based dog show some behavior where we are like, oh, that's so natural. Yeah. So gave you these examples of reinforcement learning. It's fun to see the graphics because you can sort of see, the potential where it could take us. So let's talk a little about where it is actually taking us right now. Yeah. We've seen an exponential growth in the data of AI. I think we have our own Moore's law. It's basically the amount of data being trained on doubles every 18 months or so. And it's very clear that we are running out of data. I mean, like how many times can OpenAI crawl the internet for text? I mean, like, yeah, until you crawled it all, which they more or less have, that's it. Yeah. Then they can start crawling the internet for text that ChatGPT generated, but that's not that interesting. Yeah. So what's important here is to sort of create these feedback loops, and that's what we see in large language models and in other places. This is probably a little too small to read, but I think it's very important to draw sort of from the funny videos I showed you and the entertaining videos. I want to draw you in and take you back to things like GPT or ChatGPT or GPT-4. Yeah. And large language models are really just, and I mean, like, not just in a negative way, but it's really, let's just build a model that provides a compressed version of all text on the internet, for instance, yeah, or all text in my knowledge base, or whatever I sort of suck in and build a large language model over. Yeah. So it's a compression, you have 1 trillion parameters. They capture a lot of concept and stuff in there. They are really good at compressing knowledge, and then you can decompress or uncompress that knowledge out of it again. Yeah, but it's not perfect what comes out. Yeah, it's not perfect. It wouldn't be a compression if it was perfect what came out. Yeah, and then on the second stage, there is what you can call a fine-tuning taking place. So the first stage didn't involve any humans. The second stage is actually where humans go in and rank. I think for GPT-4, they rank several millions, if not more, many millions of outputs from large language models, yeah, where you rank the good over the bad, yeah. And then, just like Google is doing, every time you click on links, the 10 blue links, they sort of constantly take that feedback in, and you help Google understand which are the good links and which are the less good links, yeah. That makes Google better and better over time by human feedback. Yeah, I actually hired a guy many years ago, 2000. I hired a guy, and he came from Google, and he was a linguist. And I said, "What did you do at Google as a linguist?" And he said, "Oh, we were hundreds of people sitting and picking, ranking outputs day long. That's all they did. They were ranking outputs so that they could actually help Google build better search results." And I was like, "Oh, I thought it was all about the PageRank algorithm." And he was like, "Nah, not enough." Yeah. So they actually, at that time, this is 22 years ago, had people sitting in the basement ranking output. Yeah. OpenAI did the same. Thousands of people, Scale.ai and other people, other companies provided that service, ranking all these. Yeah. And then comes the magic part. Yeah. Here comes the reinforcement learning part. This is where everything I showed you today is PPO. OpenAI used PPO too. proximal policy optimization. And what they do with this is they create a policy, just like the chicken can safely cross the road, no matter sort of what happens with these cars coming in. It will even stop if too many cars come in and wait until they're passed before it goes on, yeah? And you will never get hit, yeah? This is the same. You create a policy that uses the output of a large language model. You will output a lot of garbage. We all know that. They call it hallucinations or whatever, you know, they want to call it, but a lot of garbage, yeah? But if you have a policy that takes the good stuff out, the good stuff that sounds the right way, it's magic, yeah? And a lot of people, including myself, would probably have, honestly, yeah, I would have doubted that it would work, yeah? That you could actually create a policy that would take textual output efficiently and basically just use a simple policy, yeah? And I think that's a piece of magic. And what I want to say is that what they have done is fairly rudimentary, fairly mundane. I showed you examples of curiosity, and I immediately think like, wow, what if GPT-4 was curious with me? So I ask a question and it says, why, or why are you asking this question? What are you looking for? I mean, like, can you guys imagine that what we have seen so far is sort of actually pretty dumb? It's amazing, but pretty dumb. Imagine that it can get into curiosity. Imagine things like curriculum, that it can actually start building up knowledge that GPT, or when I say GPT-4, it's, you know, any of those systems, yeah. Imagine that it can start actually run experiments before it answers my question, yeah. I may ask, you know, how many people can you put in a Volkswagen, yeah, and it will, you know, run, you know, a 3D experiment and see how many can you get in there, and it will say, you know, most likely so and so many people, yeah. And I may even go out and try it in the real world and tell the system you were right or you were wrong, yeah. That's when the real magic happens, yeah. Now we are sort of getting from that Sputnik moment and somewhere towards the moon landing. I'm not saying that's the moon landing, yeah, but actually where the system starts really being interactive, yeah. So what we've seen right now is large language models and absolutely mundane 7-year-old algorithm. I think it's 7-year-old. PPO is 7-year-old, I think. 7-year-old reinforcement learning algorithm, ignoring all the research that happened ever since, yeah. And it has actually resulted in magic. Can you imagine what goes on from there on, yeah? Okay. So biology is amazing. Do not ever try to replicate the brain. It's stupid. It's computers we are talking about. They operate very differently. For years, computer vision has been about convolutional nets because that's how the brain vision system works. And now transformers work so much better. Segment anything from Meta is not using convolutional nets, yeah. So let's be careful. Let's not replicate the brain. Let's just build computers that are very smart, yeah. But let's get inspired. All these things I talked about it, you know, attention and one-shot learning and LSTM, which was very hot once. Continuous learning. Continuous learning is really, really hard. Yeah, that's why children, they learn really fast and they forget even faster. And adults, they don't forget that fast, at least early on, but they don't learn new stuff either very well. And there's a reason for that, yeah, because if you have a lot of elasticity in your weights, they quickly get overridden. That's children, yeah. But as that stiffens up, you maintain your knowledge and your skills better. But then you have a hard time learning new skills, yeah. Very difficult to bridge that, yeah. There's no easy solution. Nature didn't find a way to do it, yeah. Yeah, simulation, intrinsic values, I talked about that, all this stuff, yeah. So look around, lots of ideas, yeah. But then what I want to do is to take us a bit from biology to culture. Homo sapiens appeared in Eastern Africa 200, 300,000 years ago, spent a lot of time there, tried to immigrate out in 100,000 years ago, did not succeed. There are evidence of that. just got out and then back. There was something out there that was not pleasant or whatever it was. About 45 to 70,000 years ago, and these numbers, they change all the time. But, let's just hand wave a little. Something happened. Homo sapiens left or immigrated out of Eastern Africa, and they spread all the way, eventually, all the way to Australia, which was like really, really far away. Yeah. So that took time, but it started around that same time where we have evidence of a cognitive revolution. Yeah. At that time, 30 to 40,000 years ago, give and take, we have these cave paintings. So suddenly people at that time could imagine stuff and paint it on a wall. Or we have the lion person, which was found in Germany, which is like, I think, 34,000 years old, which is a human body with a lion head. And that's crazy stuff, yeah. Can only have been created by an artist, yeah, because it's not real. And that means that something happened. And what did happen? I think that people got a lot smarter. No, not really, yeah, because the hardware didn't get updated. Genetically, not much happened in 100,000 years, not to the brain. It's very stable. The brain, same size, same structure, same everything. So the GPU didn't get upgraded, yeah, for 100,000 years. Yet, back to the moon landing, yeah, we went from the jungle, picking berries and surviving, to putting a person on the moon with the same piece of hardware. Yeah. A lot more of us in the meantime, and this emergent behavior, language, collaboration, and anticipation. These kind of things that really separate us from a lot of other living animals. Yeah. And I think that if we look back on machine learning and AI systems, when we just have one of them, it's a little tricky. They're not very smart. When we have two of them and they start doing stuff together, it's better. Imagine that we had like 1 million of them doing stuff with feedback loops and learning and being able to run experiments and learn stuff that we don't know. Just think about DeepMind's AlphaFold. Yeah, can predict protein folding at 95% accuracy, which is scientists can do that at 50% accuracy. Yeah, with algorithms that we develop. Yeah, knowing the biochemistry and the physical chemistry going on in between these bindings that happens to attractions and the opposite between parts of a protein molecule. But DeepMind's deep neural net figured out a lot of chemistry that we are not aware of, yeah, and is able to fold more efficiently. It deeps inside the net. There are some concepts that we are not aware of in science, yeah. So imagine that we have a lot of those systems, not just folding proteins, but they build lithium-ion batteries, and they design cars, and they do healthcare stuff, whatever, yeah, and they all communicate with each other. Then that's when you go from the jungle to the moon, or somewhere worse. Yeah, who knows? So that was sort of my key talk. I do want to, and you feel free to connect, I do want to go back and just get back and talk about the internet, because I do want to say one thing that had really hit me, especially recently. And that is that what is happening right now is this Sputnik moment, is this revolution where 1 year from now, we're going to look back and say, oh my God, things really changed. And I can tell you, first time I touched, a browser, and we had web servers, and you could read one document here, and then it could link to another document over here. It was, your brain explodes. Yeah, it was like, wow. And people are going to sell books this way. Yeah, crazy. Yeah, or eBay and auctioning and so on. It was like everything's going to change. Yeah, and it did. Yeah, this is the same. Yeah. So it often makes me think of the history of Netscape. Yeah, because I talk to a lot of people right now in the AI space. They don't say it loud. They don't put it on Twitter. Yeah, but this stuff here, GPT-4 and DALL-E and Mid-Journey, has really, disrupted a lot of things. I'm from Unity, yeah, so graphical artists, game developers, they're like, oh my God, I used to be the one that did all this, and now Mid-Journey can do all the nice graphics instead. What's my job gonna be? Yeah? Good. I know it's bad, actually. And people need to adapt. Programmers need to adapt. Stuff is going on, yeah. But I can tell you that the industry that is most disrupted right now is the AI industry itself. There are thousands of AI companies out there developed in ingenious chatbot systems. I met a company recently, they showed me how they had an emotion engine for a chatbot. And they could key words and emotions together and design it all. And look, it could drive emotional reaction when you chat with it. I took GPT-4 and I said, GPT-4, you're now an NPC in a video game. I'm gonna have a dialogue with you. And every time you respond back to me in square brackets, you should also tell me how you feel. And then I said, I just gave you a robot duck. Happy, thank you very much. Go and play with it. Neutral, I'm going playing with it. I told it, oh my God, one leg just fell off. GPT-4 says back, unhappy or sad. Oh my God, what I'm gonna do? I said, I will take it in for repair. GPT-4 was happy. I mean, like, this company spent all these years. And now it's why can GPT-4 do this? Because it's human knowledge that when then these things happen, people get, happy and sad and neutral and all this stuff. It's easy. Yeah, it's just in human knowledge. Yeah. So what I think is important is the lesson that I learned when I followed Netscape very closely in those days. Yeah. So we had Netscape. Everybody remember there was a Netscape browser. Maybe you don't remember because it's so long time ago now. Yeah, there was a Netscape browser. And then even Microsoft, they put a browser into Windows by default, and Netscape was like, boom, dead, out of business. Yeah, and fell flat over because the browser, our browser is not needed any longer. The internet is over. Yeah, they fell flat when eBay was yet to be invented, when Amazon.com was yet to be invented, Facebook, Instagram, TikTok, I can name it, yeah, all these things. So my advice to both investors and founders and everybody in the space of AI, yeah, you have been disrupted more than anyone else. And be careful not to sort of double down on, back in those days, we build browsers and that the only value you can bring to the internet, or web servers, that was the other one, yeah. Or dial-up service, AOL, yeah. Or they were disrupted by DSL, which was disrupted by Comcast cable, yeah. Don't try to be Comcast for AI, yeah. That's not. So my key message is, I'm gonna end with that, I promise you now. My key message is build applications, I can tell you in 1992, I could not imagine Facebook, yeah. You're gonna find friends on the internet and stuff like that. How's that gonna work? Yeah, I couldn't imagine that, yeah. I remember meeting, I moved to the US and for a brief period, I met Pierre Omidyar at this, I went to work for General Magic and I met Pierre Omidyar there and I said, Pierre has started eBay and I said, how do you get people, how does it work? Yeah, because if I put in my credit card number, people are just gonna take my money and never send me anything. And he said, a rating system. I was like, gosh, I never thought about that. Yeah, so I mean, like, here's the internet, yeah. And I have never thought about rating systems. You know what, that rating system is so good that nowadays people will go into strangers' cars and let them drive at night to other places, yeah, far from home. called Uber, yeah, based on this idea that if you do something bad, you're going to get downrated, yeah. And if I do something bad, I'm going to get downrated. So we're all going to be nice to each other, yeah, because we both want this to happen, yeah. Stuff like that was not something people thought about in '92. Yeah. Very few people. I didn't, yeah. So I really want everybody to think or double down on this idea that large language models, yeah, we don't have to all build large language models. Very, very large computer vision models, yeah, we don't all have to build that, yeah. What we have to do is that we have to really focus on ingenious applications that the moon landing, yeah, I can't imagine what it is. That's the whole point. That's where the innovation lies, that if it's easy, if we all can see it, like, oh, large language models, I'm going to go into that business. No, it's like, I don't know, let OpenAI do that. It doesn't matter to me, but I want to use it for something. Yeah, that I think matters more than anything else. Okay, thank you.